Okay, as you noticed in the book, we're looking at equilibrium. And at its most basic, equilibrium is a state in which there are no observable changes as time goes by. Now, there are different kinds of equilibrium. Chemical equilibrium is when the rates of the forward and reverse reactions are equal, which then means, of course, that the concentrations of the reactants and products remain constant. And if you think back to the initial statement, we don't see anything going on, okay? The concentrations of the products don't change. The concentrations of the reactants don't change. Everything is constant. It's an equilibrium. It is also possible to have physical equilibrium. So, for instance, turning liquid water into gaseous water. And then with chemical equilibriums, of course, chemical changes, we're always creating something new. And so in this case, we have N2O4 switching into NO2. So what we're going to look at is some ways of explaining what equilibrium is, and hopefully that will help you with what some of the questions we're asking. Okay, concept of equilibrium. So we're going to start with an example. N2O4. Okay, it's a colorless, frozen, solid object. At room temperature, it starts decomposing and basically turns into this brown NO2. You see the forward reaction with the arrow that's going towards the right. So N2O4, colorless, solid, frozen stuff, turns into this brown gas NO2. At some time, however, the color stops changing. In other words, we don't have very much NO2 at first. So even though it's a brown gas in the chamber, it's just barely brown. And then it gets darker and darker as we make more of it. But eventually, color doesn't get any darker. And we have a mixture of both N2O4 and NO2 at that time. So we've reached chemical equilibrium. The forward reaction, in other words, N2O4 making NO2, is equal to the reverse reaction. Now, up to this point, we really haven't talked that much about having reverse reactions. We did a little bit in acids and bases, but in reality, there are lots of reactions that don't just go from the ingredients to the product and you run out of ingredients. Sometimes you get a reverse reaction too. It goes backwards the other way. And so we have two reactions going on at the same time. And as you'll see later on, we'll actually start putting in double arrows to show that it's both forward and reverse. But when those two reaction rates are equal, then we say, again, it's at equilibrium and all the concentrations, both the products and the reactants, are equal. They stay constant. Now, we're going to use the same collision model that we've been using when we had gases before. And basically, the idea is, at first, there's no NO2. So there's no reverse reaction because there isn't anything to react. But as the amount of NO2 builds up, the chance of two NO2 molecules colliding increases. Eventually, they do collide, and some of the time they will form N2O4. At the beginning, again, there's no NO2, so there's no reverse reaction. There's no NO2 going to N2O4. But eventually, there's a whole bunch of NO2, and so the reverse reaction goes along. So one of the things that you'll see is, to begin with, the forward reaction, we have a whole bunch of forward reaction because all we got is N2O4. Start making NO2. Well, the more NO2 we make, the less N2O4 we have. That reaction kind of slows down, and at some point, It doesn't stop, but it just is constant. It's not going to get any slower. It's not going to get any faster. On the other side, the reverse reaction, it starts out at 0 because there isn't any. But after a while, we've made some NO2, we've got more NO2, they start colliding with other NO2 molecules, and we develop a reverse reaction, which starts out very slow, but as we get more and more NO2, that increases. And so basically, you can think of this as a place that sells cookies. Okay? They make cookies. People come in and they buy the cookies. As they buy the cookies, of course, they run out of cookies. They got to make more cookies. Well, what would be equilibrium? Equilibrium would be they are making as many cookies as they're selling. So they always have this constant supply, okay, but they don't want to end up with too many, so they want to reach an equilibrium. They make the right amount, the customers buy the same amount, it's always staying the same, the shelves look full. Basically, what goes in goes out. So they make more cookies, people buy more cookies. Make more cookies, buy more. So again, make cookies, somebody buys them. So a way to think about equilibrium is the rate of sale of cookies equals the rate of replacing the cookies. That would be equilibrium. Last week, I went over to Fashion Fair Mall for a moment. I was going to get Cinnabon. I thought that would taste good. And I get over there, and they're like, well, we're out. Like, okay. So I just walk away, but I'm like, really? Well, what had happened was, you know, it was about a half an hour before they were going to close. They didn't want to make more because they were going to close, and, you know, they'd have these extra ones. I don't know what they do with the extra ones necessarily at that time of night, but you don't want to do that. You want to have this equilibrium with what you're producing is what you're selling. So, two reactions. N2O4 goes to NO2. But after a while, we've got a lot of NO2, and so notice NO2 is going to N2O4. Two reactions going on at the same time, and we don't want to write two reactions, so there at the bottom we have just the double arrow, implying both a forward, most of the time we're going to say that's to the right, and a reverse back to the left. At equilibrium, as much N2O4 reacts to form NO2 as NO2 reacts to reform the N2O4. The double arrow implies it's dynamic. Now, what I mean by dynamic is, if we go back to the very beginning, we said it looks like nothing's happening. Nothing's changing. That does not mean the reaction stopped happening. It's happening. It's just that the forward reaction and reverse reactions are exactly at the same pace, the same rate. So every time one of those N2O4s turns into an NO2, and NO2 is reforming back into the N2O4, one for one, the same rate. So as far, you know, if you were to measure the concentrations, everything looks the same. Nothing looks like it's happening. But the word dynamic just means, no, it's actually going on all the time, even though you can't tell. So we're going to look at a couple of examples of our starting position so that you can kind of see what we're talking about when we say that we're at equilibrium. In the first case on the left, basically we have a lot of NO2, and we don't have any N2O4, that's why it's down. And then what happens is the NO2 starts making N2O4. It comes down because we're getting rid of the reactant. We're making product. And so the green one's coming up. because we're making more of it. But at some point, after we started with just NO2, we will reach equilibrium. Now, that doesn't tell us anything about how much NO2 or N2O4 is there. All we know is once we hit that point, notice they're flat lines. That means they're constant from that point on. They're both at some constant amount. They're not changing. The one's turning into the other and vice versa repeatedly. In the second example, we start with the other one. We start with the N2O4. So it's the one that's up high, and it's the NO2 that's down at 0. But again, once we hit equilibrium, the two things are constant. And notice they don't have to be at the same constant places. We started off with different amounts of things. We get to a constant place. It doesn't have to be the constant that it was in the previous situation. And in fact, in this third case, where we had a little bit of both, again, at some point, we will reach equilibrium and they will flatten out. So when they're constant, when they don't change anymore, as far as we can tell, nothing's going on, the forward and reverse reaction rates are equal. We say we have equilibrium. Here's another analogy to think about what equilibrium means. Equilibrium is the same number of people going up the escalator as coming down. So the number of people on each floor doesn't actually change. We don't know how many people are on each floor, but since for every person that got on the escalator, somebody else got off, the numbers don't change. It's an equilibrium. Now, one of the things you noticed in the section was the equilibrium constant, and it was nice to hear that some of you figured out the exponents. Yes, whatever coefficient, the numbers in front of the different compounds, those became the exponents in the equilibrium expression. And basically, the way it works is the products go on top and the reactants go on the bottom from the forward direction. And basically what the equilibrium constant, the Kc, does is if it's a big number, it means we make a lot of product. The numerator is bigger than the denominator kind of thing if it's much bigger than 1. If, on the other hand, it's a very small number, think back to our acids and bases where we had equilibrium constants for an acid that might have been 10 to the minus 7 for how many hydrogen ions was floating around in the water. It's a very small amount. In that case, it's the denominator, it's the reactants that's favored. Water is mostly water, even though there are some hydrogen ions and some hydroxide ions floating around inside of it, because its equilibrium constant was that 10 to the minus 7 for neutral, 10 to the minus 14 for the two of them combined. So anytime you have an equation, you can find out its equilibrium constant by looking at the concentrations of the products raised to their exponents divided by the concentrations of the reactants raised to their exponents. Now, there are a couple of things that make this actually a little bit easier. For one thing, water is just 1. We don't include solids in these things, so just the liquids and the gases. So if there's a solid in our equation, then we don't worry about that. We just worry about the liquids and the gases. And again, if water is included, water is 1, and so that really doesn't impact it as well. Now, you can look up constants for different types of reactions. And then what that allows you to do is if you know what the concentration of one part is, and you know what the constant is, then you can figure out what the concentration of the other parts have to be. And you can solve for that. Okay, now equilibrium is pretty simple. Forward reaction equals reverse reaction. Doesn't look like anything's going on. Constant concentrations. What we're going to spend most of our time on is Le Chatelier's principle. In other words, hey, everything's at equilibrium, and then we're going to mess it up. We're going to change something. We're going to add more of a reactant or a product, or we're going to change the temperature, might even change the pressure. If there were gases, pressure would be affected by gases. We're going to make some change to the system. That's what's meant by the external stress. And basically, Le Chatelier figured out that the system will automatically adjust in such a way that the stress is partially offset as the system reaches a new equilibrium position. So what's going to happen is we do something, it reacts in such a way as it counteracts whatever we did. We'll go through some examples of that. And then reaches a new equilibrium, which will have different concentrations than the old equilibrium. Now, we touched on this a little bit in the last part where we talked about the acids and bases, and what we said was, hey, if we took an acid or a base and we just stuck it in water, we'd have a lot of hydrogen ions for the acids or a lot of hydroxide ions for the bases. But if instead we took that base and put it into something that was a weak acid, the weak acid would counteract some of that base, and it would not have the same pH as we just stuck it into water. In other words, a little bit of it got neutralized. So that's kind of what Le Chatelier's principle is trying to get at. The system itself will react to whatever the stress is to kind of neutralize whatever change we made. Even if our change is something like changing the temperature, it will do something to kind of make a change to that. So, for example, we have nitrogen and hydrogen gases that combine to make ammonia gas. Now, let's suppose we added some more ammonia to the system. It was at equilibrium, but now we've stressed it by adding some more ammonia. Le Chatelier's principle says basically we're going to increase the reverse reaction. We're going to try to get rid of some of that extra ammonia, end up making more N2 and H2. Basically, the equilibrium will shift to the left, and by that meaning it will have more reactant and less product to offset the fact that we added in some NH3. Now, it will not get rid of all the extra NH3 that we did, okay? But it'll offset it a little bit. It'll effectively neutralize our addition. So there'll be more ammonia than there was, but now there's also going to be more N2 and H2 than there was before because it turned some of that NH3 back into those initial reactants. And so this is what a picture would look like of that case. So flat lines, all at equilibrium, all at constant concentration. Okay, then you see the little spike for the NH3. We added some. And then notice what happens. The N2 and the H2 go up. The NH3 goes down. Now, none of them are back to where they started. But at some point, we'll hit equilibrium again. They all flatten out again. And so at that point, we have a new equilibrium. So they were at equilibrium, concentrations weren't changing, the forward reaction equaled the reverse reaction. We added in some NH3, and Le Chatelier says, you know what? You've now got too much NH3. It's going to try to get rid of some of that. Well, how does it do it? By doing the reverse reaction, by going back to N2 and H2. So their concentrations go up, the NH3 starts to come down, and eventually They all flatten out again at new concentration levels. And by the way, if we were to stick the concentrations into that equilibrium constant that we were looking just a moment ago, it would be the same value at the beginning and at the end, because everything has to adjust. It's kind of a proportional thing. Everything has to adjust in a certain way. So here's a way to summarize some of the things that are going on. If we add any products, then it's going to shift to the left. Okay, so increase concentration of products, we will shift to the left. Shifting to the left means make more reactants. If we remove product, that's a different change. We take some of the product out of there. Well, then it's going to go in the opposite direction. It's going to try to make more product. That's the shift. And so we'll say that that will decrease. We decrease the concentration of products, and we'll have a shift right. Now, what does that mean again? Okay, we took some out. We acted as an external stress. We removed some of the product. The reaction itself will then try to replace some of that product that we took away. Well, how's it going to do that? It's going to take the A and B, stick them together to make more C and D. As a result, the A and B go down, and the C and D will go up from wherever they were after our stress. So please note, when we say shift left, that means make more of the stuff on the left, have less of the stuff on the right. When we say shift right, it means you're going to make more of the stuff on the right, you're going to have less of the stuff on the left. Those are the kind of questions you're going to get asked. You don't have to worry that much about an actual concentration amount. You're going to be asked, hey, is this shift left? Is this shift right? And what does that mean? Well, it means we have more of something and we have less of something else. And the more and less are always the same kind of idea. Shift left, more of the left, less of the right. Shift right, more of the right, less of the left. So it's always going to be consistent in that form. Same thing for the other side. Okay, if I add more reactant, increase that concentration. Either one, A or B or both, then it's going to shift to the right to make more product. If I remove part of the reactants, then it would shift left to reform more reactant. So notice, always opposite. When I add, it goes away. When I remove, it comes back towards whatever I removed. Now, for gases, changes in volume and pressure affect gases from our gas laws. Changing, increasing pressure means the volume has to go down, increasing volume, the pressure has to go down. They go in reverse directions, so we can say the same things for those. So increase the pressure. Now, notice what it says here. It shifts to the side with the fewest moles of gas when you increase the pressure. Well, how do I do that? Well, basically those numbers in front of the different compounds, those are moles. So all I have to do is add them up, and whichever side has a bigger number, if I increase the pressure, I want to go to the side with the smaller number. In the example here, since there are no numbers, when there are no numbers, it's automatically 1. I have 2 moles on the left. 1 mole of A, 1 mole of B. I have only 1 mole of C. So if I increase the pressure, this one's going to mean make more C, because there's fewer moles of C, fewer things to come in contact with each other, and it's going to decrease the number of moles of A and B. So it's going to shift in that direction. If I decrease in pressure, it's going to do the opposite. It's going to go to the side with more moles. So in this case, if I decrease the pressure, I want more moles, I would have more A and B, less C. Now, volume does the opposite of pressure. So if I increase the volume, notice it went to the side of most moles. And if I decrease the pressure, it goes to the side with fewer moles. So pressure and volume do opposite things, just like in our gas laws. Pressure goes up, volume had to come down for a constant temperature. Now, a lot of reactions are exothermic or endothermic, meaning either exothermic, they produce heat as a product of the reaction, or endothermic, it needed some energy, it needed some heat to get the reaction going. Well, it turns out that if I have a change in temperature, like I change the temperature of the room in which the reaction is taking place, Le Chatelet says we want to counteract that change. So for instance, let's say that I increase the temperature. If I raise the temperature, what the reaction wants to do is counteract that by lowering the temperature a little bit. Can't counteract it altogether. Well, what that means then, it wants to go away from the side that has the heat, that has the kilojoules of energy. Well, in that exothermic case, it's going to shift left because the A side doesn't have any kJ on it. So it does not want to make as much heat because I have raised the temperature. On the other hand, if it's an endothermic reaction, where the kJ is now on the reactant side, it's going to shift right because the B side in this case is the side that doesn't have the energy or heat connected to it. So increasing temperature always goes to the side that doesn't have the heat or energy part to it. And usually there'll be some number there, like 69 kilojoules or 400 kilojoules or something like that. Sometimes it can be done in calories besides kilojoules, but that would be part of the reaction. And again, exothermic, it's on the product side. Endothermic, it's on the reactant side. Decrease the temperature, goes in the opposite direction. We want to make more kJ, make more heat, give off more energy. And so we go towards the side that has the heat, the kilojoules, whichever side that's on. Now, another way that you can change a reaction is by adding a catalyst. A catalyst doesn't change the equilibrium constant, the K, and it does not shift the equilibrium of the system. Catalyst doesn't do anything except speed the reaction up, but it speeds up both sides. It speeds up the forward and it speeds up the reverse. It just means you get to equilibrium faster, but it doesn't change where the equilibrium position is. What it does basically is lower what we call the activation energy. And the activation energy is this part right here on the screen. Basically, this is where we started. We need a certain amount of energy to break our bonds. That's what's related here. And then it goes to a lower energy state over here. Likewise, in the reverse reaction, going from C and D, they have to overcome a certain amount of energy to get to A and B. So what the catalyst did is we had this big hill to overcome. It became a smaller hill to overcome. We didn't need as much energy to get either reaction to take place. But it does not change the concentrations that they'll finally end up at. It just gets them there sooner. Again, does not change equilibrium constant. It does not shift the equilibrium. So if we said, hey, our stress was we added a catalyst, how does it shift? We would say no shift. All right, so that is our notes on equilibrium.